This is a video walkthrough for Practice 9E. For 1 through 8, we're asked to solve each exponential or logarithmic equation and write our solution in two forms, the exact or calculator-ready form and the approximate form, which is rounded to the nearest thousandth. So in number 1, we are going to begin by solving for the exponent, and an exponent equals a logarithm, and the log will be base 2 since base 2 is raised to the exponent x, and log base 2 of 9.3. That's our exact form answer. So I'm going to box that one in, then use the calculator to find the approximate value. To enter a calculator logarithm on the calculator, control button, and then the 10 to the x button. And we are entering the log base 2 of 9.3, which gives us 3.217. In number 2, we have a logarithmic equation where the variable is inside of a logarithm. In order to solve for x, we can rewrite in exponential form. The base is 7. The exponent is what the logarithm equals, so that's negative 0.23, and that's equal to x. So here we have our exact form answer, and then the solution can be rounded to the nearest thousandth by entering 7 raised to the negative 0.23, which will give us 0.639. In 3, we have an exponential equation where the variable is in the exponent, so we'll use logarithms to solve. The log base 5.7 of 49 is equal to the exponent 2 times x. Now we can divide by 2, so x is equal to the log base 5.7 of 49 divided by 2, and that's our exact form answer. Now we can find the approximate value by entering this on the calculator. To enter a fraction, control divide, and then a log base 5.7 of 49 divided by 2 gives us 1.118, which is the approximate answer. In number 4, we have a logarithmic equation, so we need to undo the logarithm first by putting it in exponential form. Base is 3, the logarithm equals the exponent, so the exponent is 1.9, and that equals x minus 2. Adding 2 to both sides, x is equal to 2 plus 3 to the 1.9 power, and that will be our exact form answer. To enter that, 2 plus 3 raised to the 1.9 power gives us 10.064 as the approximate solutions rounded to the nearest thousandth. In number 5, we have a logarithmic equation, but before undoing the log, we must divide both sides by 3, and so log base 5 of x minus 7 is equal to 2/3. From here we can put this in exponential form. The base is 5, the exponent is what the logarithm equals, so 2/3, and that's equal to x minus 7. Adding 7 to both sides, x is equal to 7 plus 5 raised to the 2/3 power, and that's our exact form answer. So we'll enter 7 plus 5 raised to the 2/3 power, which gives us an approximate solution of 9.924, rounded to the nearest thousandth. In 6, we have an exponential equation, so before we can undo the exponential expression, we must add 3 to both sides, giving us 8 to the x plus 2 is equal to 74. Now, in order to solve for the exponent, we need a logarithm. So the log base 8 of 74 is equal to the exponent x plus 2. Solving for x by adding negative 2 to both sides, we have negative 2 plus the log base 8 of 74 as the calculator-ready or exact form solution. So entering negative 2 plus log base 8 of 74, we get a result of 0.070 as the approximate solution rounded to the nearest thousandth. In number 7, we have an exponential equation, but we need to isolate the exponential expression by dividing both sides by 5 first, so 8 is equal to 1.04 raised to the x power. Now we can solve the exponent by writing in logarithmic form. So the exponent x is equal to the logarithm base 1.04 of 8. And that's our exact form solution. So entering the log base 1.04 of 8 gives us an approximate solution of 53.019, rounded to the nearest thousandth. In number 8, we have a logarithmic equation, but we'll need to divide by 2 to isolate the logarithm before rewriting in exponential form. Since there's no explicit base on this logarithm, when we write in exponential form, we assume the base to be 10. So the base is 10, and the exponent is what the logarithm equals, which is 5/2, and that's equal to x plus 1. Adding -1 to both sides of the equation, we get x equals -1 plus 10 raised to the 5/2 power. That's our calculator-ready or exact form answer, which can be entered -1 plus, and there is a 10 to the button here, which we can use. It's 10 to the 5/2 power, which is 315.228 as the approximate solution, rounded to the nearest thousandth. In 9 through 16, we're challenged to solve equations, but remember our non-calculator ways of solving them, so no use of the calculator here. In 9, we have a logarithmic equation, which we can solve by condensing the logs on the right side, or the left side of the equation. The subtraction of two logarithms is equal to the log of the division, log of x divided by 4, and that's equal to 2. Since there's a log on one side of the equation, we solve by rewriting in exponential form. The base is understood to be 10, the exponent 2, and the result is x divided by 4. Since 10 squared is 100, 100 is equal to x divided by 4. Multiplying both sides by 4, we get x is equal to 400. In 10, we have an exponential equation, which we can solve by using common base. Both 8 and 16 can be rewritten in base 2. 8 is 2 to the 3rd power, and 16 is 2 to the 4th power. When we raise a power to a power, we multiply exponents. So 3 times 2x plus 4 is 6x plus 12, and 4 times x minus 1 is 4x minus 4. Since the bases are the same on both sides of the equation, we can equate the exponents and solve by subtracting 4x and subtracting 12 and dividing by 2. In 11, we have an exponential equation that can be solved by rewriting both sides using a common base. 1/27 can be rewritten as 3 raised to the -3 power, and the cube root of 9 is the same thing as the cube root of 3 squared. Written with a rational exponent or fractional exponent, this is 3 to the 2/3 power. On the left side, we can multiply exponents when raising a power to a power, so that's -6 plus 3x, and the exponent on the right is 2/3. Now that we have a common base, the two exponents can be equated. And if you want, we can clear fractions by multiplying through by 3. -18 plus 9x is equal to 2. And now adding 18, we get 9x is equal to 20, and so x is equal to 20/9. In number 12, we have a logarithmic equation where there are 3 logs, all with the same base. On the left side, we can condense this log. The subtraction of 2 logs with the same base is equal to the log of the division, 5x plus 3 divided by 7, and bring down the log on the right side. And so if 2 logarithms with the same base are equal, then their arguments are equal to each other, so 5x plus 3 divided by 7 is equal to x minus 3. Multiplying both sides by 7, we get 5x plus 3 is equal to 7 times x minus 3, or 5x plus 3 is equal to 7x minus 21. subtracting 5x, and adding 21, dividing by 2, we get a solution of x equals 12. In 13, we have two logarithms with the same base on both sides of the equation, but we have a coefficient of 2 here, so we need to use a log property. So 2 times the log of x is equivalent to log base 3 of x squared. And what that does is it gives us two logarithms that are equal to each other. And if two logarithms are equal to each other, then their arguments are equal to each other. So we get x squared is equal to 8x minus 15. Subtracting 8x and adding 15, we get 8x squared minus 8x plus 15 is equal to 0. And that factors x minus 3 times x minus 5. So either x minus 3 is equal to 0 or x minus 5 is equal to 0, which gives us solutions of 3 and 5. It's important that we check those solutions. If we look at the original equation, if x is equal to 3, then we have 2 times the log base 3 of 3 equals the log base 3 of, and 8x minus 15 will be 24 minus 15, which is 9. Since the arguments of both logarithms are positive, we can accept that as a valid solution. Now, let's change this to x equals 5. So if we replace x with 5, then the right-hand log is 8 times 5 minus 15, which is 25, and 2 times the log of 5 is equal to the log base 3 of 25. So both solutions this time are valid, so we can accept both solutions here. Number 14, it is possible to use a property of logarithms to re-express the logarithm on the left side as the log base 9 of x plus 1 squared. However, it's also possible to divide by 2, and this is probably the easier of the two ways to solve this equation. So log base 9 of x plus 1 is equal to negative 1/2. Rewriting in exponential form, 9 raised to the negative 1/2 is equal to x plus 1. Now without a calculator, we can know what 9 to the negative 1/2 is. The denominator represents the root, so that's a square root, and then the numerator represents the power. So the square root of 9 is 3. 3 raised to the negative 1 is 1/3. So 1/3 is equal to x plus 1. I'm going to multiply through by 3. And then subtract 3 from both sides. So negative 2 is equal to 3x. And then solve for x. And x is equal to negative 2/3. For a logarithmic equation, we may want to check the solution to ensure that there are no logs of negative numbers. And if we replace x with negative 2/3, then the argument of this logarithm is negative 2/3 plus 1, which is 1/3. That's a positive number, so this is a valid solution. Number 15, we may want to spend a little bit of time finding a common base here. The 5th root of 8 is the same as the 5th root of 2 cubed, and that's equal to 2 raised to the 3/5 power. 4 can be re-expressed as 2 squared. So now we have 2 to the 3/5 power equals 2 squared raised to the x plus 7 power. When we raise a power to a power, you multiply the exponents. So the exponent of the 2 on the right is 2x plus 14. So now we can equate the exponents. 3/5 is equal to 2x plus 14. I'm going to multiply through by 5 to clear the fraction. So 3 is equal to 10x plus 14 times 5, which is 70. And now subtracting 70, we get negative 67 is equal to 10 times x. And x is equal to negative 67 tenths. In number 16, we have logarithms with the same base on the left side of the equation, so we can condense those. When two logarithms are added to each other, it becomes the logarithm of the two arguments multiplied. So x times x minus 6 is x squared minus 6x. Don't forget to distribute. And that equals 3. So now, since we have a logarithm only on one side, we can rewrite this in exponential form. So base is 3, exponent is 3, and that's equal to x squared minus 6x. Since 3 to the third is equal to 27, we can subtract 27 from both sides of the equation, and then factor x minus 9 times x plus 3. So either x minus 9 is equal to 0, or x plus 3 is equal to 0. So x is 9, or x is equal to negative 3. Let's check, since this is a logarithmic equation, to make sure that each of these solutions gives a logarithm of a positive number in the original equation. If x is 9, the arguments of the logarithm are 9 and 9 minus 6, both of which are positive numbers. If x, however, is negative 3, the arguments are negative 3 and negative 3 minus 6, both of which are negative numbers. So that is not a valid solution, and x equals 9 is the only solution. In 17 through 20, we return to calculator active questions again. The size of the rat population of a wharf area is modeled by the function r equals 200 times 2.7 to the 0.08 times t, where r is the number of rats and t is the number of years since they started tracking the population. So we are looking for, in number 17, how many rats initially lived in the wharf area, or at t equals 0 years when they first started counting. So I'm going to take my formula and just replace the t value with 0. That's already a calculator ready solution, because all the numbers have been substituted and there's nothing to solve. All we have to do is enter that expression. 200 times 2.7 raised to the 0.08 times 0, and that gives us 200 as the initial population of rats. This is actually something we could have done without a calculator, because you'll notice that this expression, 2.7 to the 0 power, is just 1. In 18, we're looking for the number of rats after 5 years. So we'll use the same formula. R is equal to 200 times 2.7 raised to the 0.08 times, and replace t with 5. This is also a calculator-ready solution, and if we want to save a little bit of time with calculator entry, you can use the arrow keys on your calculator to highlight the previous calculation, press enter, and then edit that calculation by deleting the 0 and replacing it with 5. And that'll give us, rounded to the nearest rat, 298 rats. In 19, we're looking for how long it would take, so now we're looking for the time that it would take the population to reach 360. So 360 is the value of r, so replacing r with 360 in the formula, we get 360 is equal to 200 times 2.7 raised to the 0.08 times t. This is an exponential equation, so we can start by dividing both sides by 200. And 360 divided by 200 reduces to 9/5, and that's equal to 2.7 to the 0.08 times t power. Now we can solve for the exponent by rewriting in a logarithmic form. So the exponent, 0.08t, is equal to the log base 2.7 of 9/5. Dividing by 0.08, we get log base 2.7 of 9/5 divided by 0.08. And we can start with control divide for a fraction. And the numerator is the log base 2.7 of 9/5. And then we're dividing by 0.08, which gives us 7.4 years, rounded to the nearest tenth of a year. In number 20, we're looking for how long it would take for the rat population to triple. Since the initial number of rats was 200, when they triple, the number of rats will be 200 times 3, or 600. Replacing r with 600, we get 600 is equal to 200 times 2.7 raised to the 0.08 times t. We can divide both sides by 200, which will give us 3 is equal to 2.7 raised to the 0.08 times t. Rewriting in logarithmic form, log base 2.7 of 3 is equal to 0.08 times t, and solving, t is equal to log base 2.7 of 3 divided by 0.08, and since we did a similar calculation previously, we can use the arrow keys to highlight that previous calculation, press enter, and then edit, changing that 9/5 into 3, and that will give us 13.8 years, rounded to the nearest tenth. In 21 through 22, we're using the compound interest formula to answer each question, and we have in 21 $5,000 invested initially, so that's our value of P. The interest rate is annually 9%, so that gives us our value of R, which is 9 divided by 100, or 0.09. And it's compounded monthly, so that tells us that that happens 12 times per year, so N is 12. And we are looking for the investment to reach a value of 7,000, so that's our value of A, which is the value of the investment, and we're looking for how long it would take, which is time. So we're going to replace all those values, A with 7,000, P with 5,000, R with 0.09, and N with 12, and T yet to be determined. If you want to start by simplifying the way this equation looks by finding the value of the inside of the parentheses as a decimal, that can be done, but we don't want to round that value, so we're going to leave it as 1.0075. Next, we can divide both sides by 5,000, which will give us the fraction 7/5 on the left side of the equation, equal to 1.0075 raised to the 12t power. So the exponent 12t is equal to the log base 1.0075 of 7/5, and dividing that by 12 will give us the approximate solution of 3.752, which is 3.75 years when rounded to the nearest hundredth of a year. In 22, we have a similar question. $400 is the initial amount, so that will be P. 6% is the interest rate, annual, so that's R equals 0.06, and it's compounded quarterly, which means N is equal to 4 times per year. Now we're looking for the investment to double in value. If the initial investment was $400, when it doubles, A, the value of the investment, will be $800. So we're going to set up a similar equation. So 800 is the value of A, 400 is P, and our base here is 1 plus 0.06 divided by 4 raised to the 4t power. Now again, we can rewrite the base as a decimal, and 1 plus 0.06 divided by 4 is 1.015. Dividing both sides by 400, 2 is equal to 1.015 raised to the 4t power. Rewriting this in logarithmic form, we can solve for the exponent. So the exponent 4t is equal to the log base 1.015 of 2. Dividing both sides by 4, we get a calculator-ready form of log base 1.015 of 2 divided by 4, which gives us that number, which rounded to the nearest hundredth of a year is 11.64